Well, welcome to Lecture 20 in Topology. So at this point in the course, I have to face facts. I don't have time to prove everything. So I will be going at a slightly more brisk pace. I think essentially we're doing Chapter 6 in this video. But I want to hit the high points and make sure that you're at least introduced to the terminology. That's kind of more my game plan here. But let's get into it. So a topological space is second countable if the topology admits a countable basis of open sets. All right, so countable meaning either it's bijective correspondence with the natural numbers or it's finite, right? So there's that. I think pretty much most things you can think of are second countable. All right, anyway, a topological space, not everything is though. A topological space is called separable if it contains a countable dense subset. So the subset being dense means if you take the closure of that subset, you get the whole space, right? So for example, the real numbers are separable because the rational numbers are countable and they're dense in the reals, right? Lemma. Every second countable space is separable. Lemma 6.7. Any separable metric space has a countable basis. Let's see here, what's next? Example. So this is L2, the square summable sequences, I guess. And let's see here. So we've got, scooch this up here a bit. L2R is a set of real sequences such that the sum of the squares of the sequences is less than infinity. And you can prove that that forms a metric space. All right, it forms a metric space via the distance function norm of a minus b, where the norm is defined to be the square root of the sums of the squares. Oopsie. Oh, my bad. Oh man, what's going on with this? That's a square up there. It's a square. That's a square we cannot spare. Let's see here. Anyway, the set of eventually null rational sequences are dense in this thing, which kind of makes sense. I mean, like you can, any real number you can approximate, right, as like an appropriate series of rational numbers. So kind of makes sense that has a shot of working. And excuse me, drinking this tea here. I have some kind of cough. I hope it's not going to develop into something worse. But anyway, here. So since that's it's rational, right? So it's countable, countably dense set. That means that L2R is separable. And then if you believe lemma 6.7, that implies that L2R has a countable basis. And of course here we mean, when I say basis, I'm talking topologically, all right? So let's see here. In a second countable space, every open cover admits a countable subcover. So that's kind of it's reminiscent of the definition of compact, right? But a little bit different. Because a compact space is one which every open cover admits a finite subcover, right? So I suppose that means a compact space. Well, anyway, of course a compact space admits a countable subcover as well, because finite's a special case of countable. But anyway, a topological space satisfies the first countability axiom, or is first countable, if every point admits a countable local basis of neighborhoods. So that's first countable axiom. Metric spaces are first countable. The proof is, I'm not doing too many proofs in this lecture, but here's one which I thought I could fit in. So to see that any metric space is first countable, if you pick a point x, you can study the open balls of radius 1/2 to a power And that you can prove gives a local basis in neighborhoods at X, but X being arbitrary, you've just proved that, the metric space is first countable. So it's kind of nice. Metric spaces are just super nice though anyway. In a second countable, locally compact Hausdorff space, there exists an exhaustion of X by compact sets. So let me review that. Second countable, locally compact Hausdorff space, there exists an exhaustion of X by compact sets. That is, you can find, well, an exhaustion. All right. Let's move on here. I guess if we've forgotten what locally compact means, we could look it up, right? Let's see, let me just take a second to do that. Come on, book. Do your thing. No, index, you have let me down. How about compact? Oh, local 98. Ah, phew, phew. I was worried there for a second. Definition 5.23, there's your definition of yield, local compactness. A topological space is locally compact if every point has a compact neighborhood. So there you go. That's what we meant by locally compact. I forgot. Let's see here. Page 2. All right, so just remember, we're going to refer to second countable and first countable at various points in this lecture, so just had to throw that out there. I'll probably come back to it if we forget, but hopefully we will not forget. And here we go, sequences. So what is a sequence? A sequence in a topological space X is a map from the natural numbers to the space. All right. And a sequence, you can talk about a sequence converging to a point, right? That means that for any neighborhood U of the point, you can pick n sufficiently large so that the whole tail of the sequence is in the open set, right? To say P is a limit point to the sequence means that for any neighborhood you pick, and for any n you pick, you can always find n larger than that n, for which the a sub n is in the set, right? So sometimes you can say a limit point is like, it's a point where you've got infinitely many points in the sequence near that point, right? And so sometimes it's also called an accumulation point. And I say near, but near kind of begs the question of metric or metricity. Metricity? What am I? Sorry, Megamind or something. Take you to shul. No, so I mean, I don't know. Closeness is maybe the wrong word, but in the context of metric space, that maybe is a good word. But anyway, metric spaces are what underlie the intuition for all of these terms, and ultimately, of course, excuse me, the bedrock of all of this is just, of course, studying the real numbers and their properties, right? In any event, sequential limits are unique in a Hausdorff space. Let's see why. That's another proof I think is important to see. Because we'd like to have limits are unique, right? And so sequential limits are unique in the context of Hausdorff spaces. And I'm not claiming that they're necessarily not unique outside the context of Hausdorff spaces. Minetti doesn't get into that, and I haven't taken the time to research that at the moment. It's not something I remember off the top of my head. But I know that studying uniqueness of limits in arbitrary topological spaces is an interesting and somewhat nuanced question. So here's the proof that they're unique in a Hausdorff space. So if you have a sequence that converges to a point P and a point Q where they're not equal, then what that means is that there exist U and V open such that P is in U and Q is in V, and they separate P and Q, right? And since AN converges to P and AN also converges to Q, that means that there exist integers sufficiently large such that the sequence fits into U and V respectively, right? Right, AN is in U for all n larger than n, and AN is in V for all n larger than m. So if I take the max of those and I look at n beyond that, then for those positive integers, a sub n is in both U and V, and therefore it's in the intersection. But that's a contradiction because we have that the intersection of U and V is empty, right? Because it's Hausdorff. and therefore we can't assume that the sequence converges to two distinct points. We get a contradiction in this way. Therefore, the limit is unique in a Hausdorff space. And of course, I'm talking about the sequential limit at the moment. A sequence, an in X is said to be convergent if it converges to some point P in X, and when X is Hausdorff, we can say that P is the limit of A sub n and write A sub n goes to P, or the limit as n goes to infinity of A sub n is equal to P. And I say the limit because that makes sense, because as we just explained, it's unique, right? In the larger context, you should just say it's a limit, because the limit, if it exists, may not be unique. Although I don't have any evidence for that, I'm just telling you it's the case. All right. Let's see here. So next up, subsequence, right? So a subsequence of a sequence is the composite of a sequence with some strictly increasing function k. But I usually think of it as taking a selection of a subset of a sequence, which is without end, but this is a fancy way of saying that. And lemma, let A sub n be a sequence, then there exists a subsequence A sub kn, k of n, converging to P. All right, if there exists a subsequence like that converging to P, then P is a limit point for A sub n, which is not to say that the limit of A sub n is that. It's just to say it's just to say that P is a limit point, right? So, because you can have the classic plus minus 1 to the n. It's got two limits points, right? 1 and minus 1. Of course, the constant sequence 1 limits to 1. The constant subsequence minus 1 limits to minus 1. So you have two limit points for the minus 1 to the n sequence, which of course is not convergent, even though it does have two limit points. All right, so anyway, the proof is, here's kind of a picture of it. So this is a subsequence, right? It's limiting to this point P, and we're claiming that it's necessarily the case that P is a limit point, right? Which is to say that you can take any open set around P, and you can pick integer sufficiently large so that you have the sequence in that, beyond that point. So you have a point in the sequence beyond that. All right, so here's a sketch of a proof that U be a neighborhood of P by definition of the A sub km. By definition of the subsequence converging to P in X, there exists an n such that A of kn is an element of U for all n beyond big N, right? So if we let m be an integer and choose m to be the max of k of n and m, then I say that implies that am is in the set U, and that suffices to prove that P is a limit point. So basically that. Let's see here. So next up, proposition 6.18, we have a countable, first countable space, a subset of that space, and then for the following are equivalent for a given point in the space. 1, there exists a sequence with values in A which converge to X. 2, the point X is a limit point of an A-valued sequence. And then point 3, the point X belongs to the closure of A. The proof of the equivalence of these three is given on page 110 of Minetti. And I would just point this out. In some analysis courses, you actually might see the closure of a set A given as being defined to be the set of all limit points of A, right? Whereas here in topology, open sets are basic and sequential. The sequential idea is secondary, right? So like for us, the closure is defined in terms of the intersection of all closed sets which contain the set. Whereas in an analysis course, the closure might be take the set you're given and adjoin all possible limit points to the set. So complementary ideas, right? And that is the part of this equivalence right here. All right, so moving on here. So continuing our tour of sequences in topological spaces. Let's see, what else can we say here? In a compact space, any sequence has limit points. And here's the proof, which I thought was interesting enough to include. So here it is. Let X be compact and A a sequence, okay? For every M, we can define Cm to be the closure of basically the tail of the sequence, right? And so that's a closed set. It's a subset of X. And let's see here. X, an element of X, is a limit point for A if X is an element of Cm for every M. Is something you can see. Now, notice here that the Cm are compact because they're let's see. Well, they're a subset of they're a closed subset of a compact space, so I believe that makes them compact. Anyway, definitely got a countable descending chain of non-empty closed sets. So then by that proposition 4.46 we talked about a while ago, back in the compact section, we have the intersection of these sets is non-empty, and so that means that X, there's some point which is common to all of these, which is to say that there exists a limit point to the sequence A sub n. So it's kind of, I thought the proof was interesting in that it combines a lot of different ideas, that we've seen. But yeah, in a compact space, any sequence has limit points, which isn't to say that any sequence converges, right? Just that it has limit points. So, so I think every sequence which converges has a limit point, right? However, not every sequence with limit points converges. Okay, so anyway, you also have sequences which don't have limit points or converge, right? They just kind of wander off and never really settle in one place, Let's see here. Let's see here. A space X is sequentially compact if every sequence has a convergent subsequence. And so again, this is the definition you might see of compact in a, in an analysis class. If you're using sequences to meet your basic, means of analysis of sets, right? So that's sequential compactness. Every sequence has a convergent subsequence. Now, a first countable space is sequentially compact if and only if every sequence admits a limit point. In particular, any first countable compact space is also sequentially compact. So the proof is given on page 110 of Minetti. We also have the following equivalence in a second countable space. X compact, every sequence in X has a limit point, and 3, X is sequentially compact. So these are, in a second countable space, we have equivalence of this, this, and this. So in general, I should mention, sometimes these things are like staggered in one direction but not the other. But this one, they're just genuinely different ideas in the abstract. So like compact does not generally imply sequentially compact, and sequentially compact does not generally imply compact. Actually, Minetti has a pair of exercises which illustrate examples where you have something that's compact but not sequentially compact, and something else that's sequentially compact and yet not compact. So here, I mean compact in the topological sense, right? Whereas sequentially compact is really compact in the sense of, well, a typical analysis course. So that brings us to section 6.3, which is on Cauchy sequences. So here, this is kind of a, so here's the thing. I didn't take a second. I was going to go and look and see if anybody defines Cauchy sequence outside the context of a metric space, Is it possible to define a Cauchy sequence outside the context of a metric space? I don't know. The idea of a Cauchy sequence is that if you go far enough out in the sequence, you can make, you can make members of the sequence as close together as you want. So I don't know if there's a way to capture that with just sets, or maybe it's just too cumbersome to be useful. But here's the definition that I'm used to, which is in a metric space, a Cauchy sequence. If for any epsilon greater than 0, there exists an integer n, such that whenever you've got n and m beyond big N, you have the distance between an and am is less than epsilon. So, and let's see here. You can also repackage that in terms of like a limiting procedure. That's sometimes helpful, right? Like you could reasonably rewrite this condition as the limit as, say, n goes to infinity of the distance from a sub n to a sub m equals to 0, right? So for fixed m. This criteria here is another way to look at Cauchy, like that, if you want to look at it in terms of a limiting procedure. But anyway, I've seen that sometimes. And anyway, so another theorem we can say, if you have a sequence which converges, then it's a Cauchy sequence, all right? And so here, of course, I mean converges in a metric space, because otherwise I don't have a definition for Cauchy sequence. But here's the standard proof. Suppose your sequence goes to L, let epsilon be greater than 0, there exists n such that the, you're within epsilon over 2 distance from the limit point for the sequences in that ball. And that's just another way of writing the distance from L to a sub n is less than epsilon over 2, right? Then we can apply the triangle inequality and notice that the distance from a sub n to a sub m is less than or equal to the distance from a sub n to L plus the distance from L to a sub m, which by construction is less than epsilon over 2 plus epsilon over 2. And as such, as long as m and n are sufficiently large, right? Thus, thus it's a Cauchy sequence, right? Because you just showed that if you go far enough out, the distance between elements of the sequence is as small as you'd like. All right. So yeah, it's a Cauchy sequence. Now, let's see here. A Cauchy sequence is convergent if and only if it has limit points. In particular, any Cauchy sequence in a sequentially compact metric space converges. All right. Now, what else? And here's the proof. Suppose you've got a Cauchy sequence in a metric space, right? And suppose a sub n has limit point p. By the Cauchy condition, given epsilon greater than 0, we may select a n integer sufficiently large such that whenever you take integers m and n sufficiently, bigger than n, you get that the distance between them is less than epsilon over 2. But then since p is a limit point, we also know that there's a big M greater than big N, for which the distance from P to AN is less than epsilon over 2. So then apply the old triangle inequality to get the distance from P to AN is less than this plus that, which is by construction epsilon over 2 and epsilon over 2, which of course is equal to epsilon for every N greater than M, which then proves, of course, that the sequence converges to P. So, yep. So there's that. Just kind of neat. Now, that doesn't quite square with what I remember, though, because honestly, folks, I'm not a topologist. I know a little bit of topology, and I've talked about this stuff to students for a while, and some of my research touches on topology, but, I'm not wired like a topologist. Those people, live it and breathe it, I'm not that. But when I hear sequentially compact metric space, that's not familiar territory to me. I guess I'm more of an analyst in the sense that I think about metric space as being complete, and a complete metric space is one in which every Cauchy sequence converges. So that's often useful in applications of analysis and other things, because sometimes it's pretty simple to prove something's Cauchy, whereas it might be a little fussy to prove it converges. But if you're in a complete context, if you've proved it's Cauchy, well, voila, you proved it converges, right? for example, if you've ever seen me prove the existence of the matrix exponential from an analysis perspective, usually I prove that the series, this is all following, these arguments I've all gotten from my advisor, prove that the, sequence of partial sums for the norms of the matrix exponential is a Cauchy sequence of real numbers, and that gives you the convergence that you need of the norm, which then in turn, anyway, it's not uncommon to use Cauchy as a criteria to prove convergence in a complete space. But anyway, here, lemma 6.21 indicates every compact metric space is sequentially compact. And we find from lemma 6.25 that every compact metric space is complete because we just got that the previous lemma that I just put over there. Cauchy sequence is convergent if and only if it has limit points. And then in particular, any Cauchy sequence in a sequentially compact metric space converges, which means that, well, any Cauchy sequence converges, that's completeness, right? So, yeah. So some very much not compact examples of complete metric spaces follow, all right? So, great. Let's see here. So the Euclidean spaces Rn and Cn are complete metric spaces. Here's the proof from Minetti. I'll just echo it here. So we'll focus on Rn because C is just R2n, right? You can identify it as such anyway. Euclidean space. And let's see here. So take a Cauchy sequence in Rn and choose n such that for n beyond that point you have distance 1 for all n bigger than n, all right? So we can do that because it's Cauchy, and then he says construct R to be the max of the norms of the elements of the sequence all the way up to n. And then he's like, okay, so this being less than 1 implies, in fact, that the range of the sequence is a subset of the compact space, like this. So if I look at the R plus 1 disk, if you will, or closed ball in Rn, then because the distance between successive elements of the sequence can't be larger than distance 1 apart, means that if I take the furthest of the sequences that we get from the origin, right, then surely you can't go more than one more unit away from the origin. And so it makes sense that this closed disk would contain the whole range of the sequence. Don't ask me to visualize it. This is an Rn, right? Okay, so then you can apply lemma 6.25 to get that A sub n converges, because you just got that it was, it's a Cauchy sequence in a compact in a compact space. So it said anyway, in particular, like we said, a Cauchy sequence in a sequentially compact metric space converges, so you get the sequential compactness inside D. And so that implies then that Rn is complete because we just took an arbitrary Cauchy sequence and we show that it converges, right? Now I will say, this proof is snazzy and stuff, but I do give a low-tech proof of this in advanced calculus, which people without topology can do, and it's just, just some hand-to-hand combat with some inequalities. Is not too bad, really. If you're interested in that, you can give me an email, I'll find it. But I think if you took a course with me already, you may have seen the proof of, like, if you've proved that R2 is complete in the way I'm thinking of, then you can easily adapt that proof for R3 or matrices or whatever. Anyway, so basically the completeness of R implies the completeness of Rn in my other proof. Here, of course, this truth is descending from, this rather abstract topological approach to things, right? But anyway, so proposition 6.29, a subspace in a complete metric space is closed if and only if the subspace is complete with respect to the induced metric. So that's interesting. So we have complete subsets, complete subspaces of a complete space, provided that we don't do something funky with the metric, right? The metric's got to be the inherited metric from the parent space. All right. So moving on here. Section 6.4 is on compact metric spaces. So let's talk about that. This is really more or less just summary here, this page, all right? But I feel like it's important. I think you should at least hear these words before you get to graduate school and experience it in a course. And if you guys already did this in Reals, then my apologies, but I don't think you did. So anyway, a metric space is said to be totally bounded if it can be covered by a finite number of open balls of radius r for any positive real number. So like a totally bounded metric space is bounded. You can just kind of take the max over a finite number of balls, so you kind of see the boundedness from that. Lemma 6.31, every sequentially compact metric space is totally bounded. Every totally bounded metric space is second countable. In a metric space X, the following are equivalent. Let's see if I can make sure I got that all in frame. I think I'll just scooch this up here just a bit. Well, hopefully you've got the definition of totally bounded already, whatever. So in a metric space, the following are equivalent. X is compact. Every sequence has a limit point. X is sequentially compact. And X is complete and totally bounded. Furthermore, if any one of the above holds, then X is second countable. Yeah, so totally bounded is another way of getting at compactness, is what this means in some sense, right? So, and let's see here, a subspace A in a metric space is totally bounded if and only if the closure of A is totally bounded. Finally, a subspace A of X is relatively compact if it's contained in a compact subspace of X. All right, and then corollary 6.36. A subspace in a complete metric space is relatively compact if and only if it is totally bounded. So this idea of total bounding, you can see it's a nice thing to play with, right? Because it's just something about this, you know, it's very concrete in some sense, right? Like you've just got this finite number of open balls of radius r, right? So you got that criteria, and you can use this sort of characteristic, you know, diameter of the balls to do kinds of arguments and estimates that span over the whole space, and it's just kind of another way of getting at that finite subcover idea, right? But more explicitly tied to the notion of distance, right? So total boundedness is an important idea if you're going to study analysis more deeply. Now, all right, so I should move on here. So we start in this chapter 6 by talking about sequences, but ultimately sequences fail because not all the, you know, the concept of a sequence is, you know, it's fine if you've got a first countable space, but you don't always have a first countable space, and so sometimes you need certain problems require a concept which is deeper and more versatile than a sequence. Sometimes sequential limits are insufficient to capture the data that you're interested in. So what's beyond a sequence? Well, there's really two directions you can go, I think. You can talk about nets, or you could talk about filters, or perhaps ultrafilters. And anyway, I don't have anything to say about filters and ultrafilters in this course, I don't think. I will say this, there is a vast and well-written literature on these things. If you look up the, there's some articles that Pete Clark wrote, I think, which are helpful. You know, I think in a perfect world I would have gotten one of those articles out here and spent a couple lectures, you know, tearing it apart or, you know, whatever. But sadly, the spirit is willing, but the flesh is weak, and so here we go on. But I should mention I just skipped sections 6.5 and 6.6 and 6.7, which concern bare spaces and completions. So and that's actually kind of important, the part I'm skipping over, in the big scheme of things, right? Because let me just talk a little bit about that. What's a completion? So if you have a metric space which is not complete, right? So in other words, you have Cauchy sequences which for whatever reason converge to points which are outside your space, right? So that you use, for example, the rational numbers is what I was come back to, right? You have lots of sequences of rational numbers which converge to real numbers which are irrational. And so what do? Well, one thing you can do is take that, incomplete metric space and do what's called complete it. And so to complete a metric space, you can adjoin all the limit points to Cauchy sequences, right? And in so doing, you get a complete metric space, and that's called the completion. So sections 6.6 and 6.7 formalize that notion, I believe, and they prove ultimately that for a given metric space, there is a unique completion. However, beware that there's not always a unique metric. So, for example, the rational numbers can be completed in one way to give the real numbers, but with respect to a different metric, not the Euclidean metric, but I think you call it the p-adic metric, you can complete the rationals to these p-adic integers or whatever they're called. And that's a quite different space than the real numbers, which is interesting to number theorists and such. So if you've never read about p-adics before, it's something that might be worth reading about just to be aware of them, because they're really different and yet they're really the same. So anyway, I don't think that's in Minetti. That's just things I've picked up, right? Minetti's mostly just formalizing the notion of a completion and then proving that it's unique in those sections I'm skipping. So anyway, and of course discussing Bayer's theorem there, which is about meager and nowhere dense sets. But let me not talk about that because my knowledge of it is very meager. Sorry. I wish I wasn't so dense. I'm sorry. These jokes are horrible. Let me go on. So a net. What is a net? Well, basically it's just a sequence where you replace the integers with a directed set. That's all it is. What's a directed set? Well, a directed set is it's a set with an ordering in this sense, right? So for every pair I and j in the set, there exists h such that it's bigger than I and j. Equivalently, you could say a directed set is an ordered set in which every finite subset is upper bounded. So I do think that there's more baked into this, and that goes back to the foundations chapter, which I'd rather not do at the moment, but it's an ordered set which has this property, right, a directed set. So some examples, of course, this has to reproduce the concept of a sequence. So if you take the natural numbers, you get a directed set with the standard order. If you take n-fold Cartesian products of the natural numbers with itself, you get a directed set, where he's defined this n-tuple to be less than or equal to that n-tuple, if and only if every component is less than or equal to every corresponding component. And this is not what I expected, by the way. Like usually when I look at in topology, there's something called you can give Cartesian product of sets. You can order them using the dictionary order, the lexicographic ordering. And lexicographic ordering wouldn't insist that this is true all down the line. Like basically, it's staggered. The first, it's just like alphabetical order, right? If the first letter of this one starts with A and the first letter of that one starts with B, then game over. It doesn't matter what happens after that, right? This comes before that. So this could be A, Z, 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 and this could be B, A, and it would still be that this is less than that in the dictionary ordering, right? But this is not that. This is anyway, it's not the ordering I expected. So he doesn't do anything with it anyway. It doesn't matter, but just saying. You can also take the set of finite subsets of a set A, ordered via an inclusion. That gives you an ordered, the directed set. And this is not a vain speculation here. This is not a like, oh, look at me, I'm a cute example that I don't come back to. He does deep things in the proof with this construction, which I will not cover. You can talk about the neighborhood of subsets, the set of neighborhoods of a point in a topological space, and then you can give the order relation set U is less than or equal to set V if V is included inside U. Look at that switcheroo. So you got to think about that. If you think about it for a little bit, it'll make sense to you why that would be what you'd want for the ordering of subsets like that. Let's see here. A map P from J to I between directed set is called a cofinal that's just an awesome thing to say. Cofinal morphism. A cofinal morphism if it preserves orderings. So P of J greater than or equal to P of J prime if J is greater than J prime. And for every I there exists a J such that P of J is greater than or equal to I. So this is a cofinal morphism. And I only mentioned cofinal morphism because it comes up again over here somewhere. Let's see here, otherwise I'd skip it. But anyway, a net in a topological space X is a map F from a directed set to X. Just like I said, it's a sequence where you replace the integers with a directed set. That's it. And so a sequence is a net. He mentions that if you take a function from nn to x with that, given that weird non-lexicographical ordering I mentioned, then this is a net, and he said that's where the term net originates. I think more so maybe n equals to 2, and also in the theory of integration, because that's where you end up with like double sequences, which are they're intertwangled, but in a kind of conniving way as you set up integration regions, which involve x's and y's both going to the number of things going to infinity, and you have to do them both at once, and you can see how that would lead to this net idea. But anyway, you can define convergence, and you can define limit point, and it's really just very reminiscent of the definition we gave for sequence. It just now, instead of working with integers sufficiently large, you work with indices, in your directed set. So, say the net F converges to X if for any neighborhood U of the point there exists index I such that Fj is an element of U for all j larger than I, and it's a limit point for a net F if for any neighborhood U of the any neighborhood of X, and for any I in the index set there exists a j larger than that I, such that f of j is in the index set. So I mean, I tell you, it's just really just intuitively the same definition as was for sequences, just replacing the concept of integers with the concept of the directed set, and using the neighborhood concept to capture closeness. Because there's no metric space here either, right? So, I guess. Just a second here. Oh, I don't guess there was a metric space in our definition of sequence either, was there? So this section on Cauchy's got me all twisted, doesn't it? Let's see here. Here's the definition of sequence back from page 2. It's like a whole half hour ago. Yeah, there's no, excuse me, there is no metric in here, right? It's just a topological space, and we have integers. But the thing is, we can always just do bigger than an indice and so forth. But I guess it's also neighborhood U of P. It's just, see, if I'd use the neighborhood notation back here, it'd even be more apparent that it's the same definition. Really just twist it a bit. All right, anyway. So a converging net must converge to a limit point, but a limit point isn't necessarily a point to which the net converges. That was the same as the situation was for sequences. Every convergent sequence has a limit point. However, every sequence which has a limit point does not necessarily converge to said limit point. Let's see here. Lemma 6.60. You got yourself a net. X is a limit point for f if and only if there exists a cofinal morphism from J to I such that the composite of the net with the morphism converges to X. So, interesting. And then finally, a few more facts to spit at you here. Proposition 6.61, let A be a subset of a topological space X for any point X in X. The following are equivalent. There is a net in A that converges to X. There's a net in A with limit point X. The point X belongs in the closure of A. So there's that. Right. Let's see here. Then theorem 6.62, a topological space X is compact if and only if every net has a limit point. That seems a little less nuanced than our previous theorem about compactness and sequentials and sequences, right? Like, what was the deal with the corresponding theorem for sequences? See if I can find it right quick. Topological space is compact. What do we have? Where was it? Well, we had, here's one of the theorems we had. In a metric space, X is compact is equivalent to X is sequentially compact, right? So that was in the metric space, right? Maybe that's, I don't know if that's the closest we can get, but notice that there's no assumption of metric space here, right? It's just a topological space is compact if every net has a limit point, right? So no need for metric space here. And a pretty neat example is given in Manetti here. This is a topological vector space V is a vector space with Hausdorff topology where vector addition and scalar multiplication are continuous. Manetti on page 127 and 128 sketches an argument via nets to prove that every finite dimensional subspace of a topological vector space is closed. So it's kind of neat. I have a suspicion that that might actually be helpful to a problem I have in the topology of supermanifolds that I'm a little stuck on. Because, well, anyway, I could tell you more about that later if you're interested. So that's it for chapter 6. Up next, we will cover chapter 7 next time. So thanks, everybody. And I should have test 2 to give you pretty soon, by the way. So thanks, guys.